In this slide, we'll introduce a problem where a linear line is not a good solution to the data given to us. Let's focus on this figure. The dots are the data x and y given to us, and it is obvious that if we try to fit a linear line along this, it will not do very well because the data actually curves down and go up again. Maybe a function with quadratic powers would be better. In such a case, the problem is still not lost. We still can cast our problem to a linear model. What do I mean? Let us now try to create a linear model such that y, the dependent variable, is a function of the independent variable x in this kind of equation where betas are the parameters of the models, f are some known function, predefined known function. You'll realize that when we cast the problem in this form, the model is still linear because the problem is still linear in the unknown parameters. And when the problem is cast this way, the resultant model still looks like this. It is the design matrix multiplied by the unknown parameters of the model beta plus the residual. You'll realize that once the F0, F1 and Fk's are fixed, then the design matrix X is fixed. The only unknown in this case is beta. Let us see some example. In example 2, we are given X and Y, and again the dots represent the data points given to us. In this case, we know that we should have an equation that have some quadratic forms. Let us assume that the model that we want to find looks like this, where y is the dependent variable, x is the independent variable, and betas are the unknowns. When you cast the equation in this form, then the design matrix is simply this. The first column represents 1 times beta 0. The second column is x1, beta 1 times x1. The third column is beta 2 times x1 to the power of square for the first entry, y1. What about the second entry? Well, if you plug in this equation, the second entry would look like y2 is equals to beta 0 plus beta 1 x2 plus beta 2 x2 square. Now, if you study this matrix notation, this is y2, this is 1 times beta 0, so we get the first entry correct. The second one is x2 times beta 1, which is this element here. And then the last entry is x2 square times beta 2, which is this guy. Now you'll notice that we add the epsilon 2 to represent the error. So if you observe this matrix notation representation along with the systems of linear equations, you will understand the complete relationships, how we got all this from this model. From the engineering perspective, of course, trying to find a model that looks like this is a very difficult problem. But if the model is given to you, then estimating beta 0, beta 1, and beta 2 is not difficult when we cast it into this least squares problem. In the tutorial, we'll give you 2 questions which allow you to have more practice. Thank you.